Hi, my name is Brian Caffo, and this is the Expected Values lecture as part of the Statistical Inference course on Coursera, which is part of our data science specialization. This class is co-taught with my co-instructors Jeff Leake and Roger Peng. We're all at the Johns Hopkins Bloomberg School of Public Health. This class is about statistical inference, the process of making conclusions about populations based on noisy data that we're going to assume was drawn from it. The way we're going to do this is we're going to assume that populations and the randomness governing our sample is given by densities and mass functions. So we don't have to talk about the whole function, we're going to talk about characteristics of these densities and mass functions that are characteristics then of the random variables that are drawn from them. The most useful such characterization are so-called expected values, though we've also covered some other characterizations, for example, sample quantiles. Expected values, the mean is the most useful expected value. It's the center of a distribution. So you might think of as the mean changes, the distribution just moves to the left or the right as the mean of the distribution moves to the left or the right. The variance is another characteristic of a distribution, and it talks about how spread out it is. And just like before, in the way that the sample quantiles estimated the population quantiles, the sample expected values are going to estimate the population expected values. So the sample mean will be an estimate of our population mean, and our sample variance will be an estimate of our population variance, and our sample standard deviation will be an estimate of our population standard deviation. The expected value or mean of a random variable is the center of its distribution. For a discrete random variable x with a probability mass function p of x, it's simply the summation of the possible values that x can take times the probability that it takes them. The expected value takes its idea from the idea of the physical center of mass. If the probabilities were weights with were bars where their weights were governed by the value of the probability, and the x was the location along an axis that they were at, the expected value would simply be the center of mass. We'll go through some examples of that in a second. This idea of center of mass is actually useful in defining the sample mean. Remember, we're talking about in this lecture the population mean, which is estimated by the sample mean. But it's interesting to note that the sample mean is the center of mass if we treat each data point as equally likely. So in other words, where the probability is 1 over n, and each data point xi has that probability. If we were to then find the center of mass for the data, that is exactly x bar. So we intuitively use this idea of center of mass even when we use a sample mean. So I have some code here to show an example of taking the sample mean of data and how it represents the center of mass just by drawing a histogram. So here I have this data Galton, and again the code can be found in the markdown file associated with the slides that you can get from GitHub. So here in this case we have parents' heights and children's heights in a paired data set, and here I have a histogram for the child's height, and here I have the histogram for the parent's height, and I've overlaid a continuous density estimate. So I'd like to go through an example where we actually show how moving our finger around will balance out that histogram. And fortunately in our studio there's a neat little function called manipulate that will help us do this. So I'm going to load up manipulate, and then the code, I'm going to show you it here, but I think if you go on to take the data products class, which is part of the specialization here, we'll actually go through the specifics of how to use the manipulate function. But here I'm just going to do it to show you it running, and then we're going to look at the plot. Okay, so here is the plot of the child's heights. It's the histogram, and I've overlaid a continuous histogram on top of it. And here, let's say this vertical black line is our current estimate of the mean. So here it's saying that the mean is 62, and it gives us the mean squared error. That's sort of a measure of imbalance, how teetering or tottering this histogram is. Now notice as I move the mean around, which I can do now with manipulate, let's move it more towards the center of the distribution. Notice the mean has gone up. Let's move it right here. Notice the mean went up to 67.5, but the mean squared error dropped quite a bit. It helped balance out the histogram. That was almost the point where it would balance it out perfectly. And you can see as I get here, it goes down a little bit more, but then at some point it starts going back up again. So if I move it all the way over here, right, this mean squared error, this measure of imbalance, gets quite large. So again, this is just illustrating the point that the empirical mean is going to be the point that balances out the empirical distribution, and we're going to use this to talk about the population mean, which is going to be the point that balances out the population distribution.